Okay. Okay, so yeah, obviously last week I was deathly ill, so we didn't have class. Did have a small question and answer session last Thursday. So today we're more or less we had like 2 lectures planned out for how do you do fluids, so it's kind of getting squeezed a little bit into one. Okay, so let's go ahead and talk about the midterm real quick. So it's going to be posted on Thursday by 9 o'clock a.m. and you'll have 48 hours to complete it. So it'll be due before 9 a.m. on Saturday morning, which means that I don't think that you guys should be doing the midterm on Saturday morning. Do it by Friday night and submit it that way. It's there's no problems because it's not like a 1 hour exam is done. Okay, it is taking the place. There's no hybrid topics this week because I'm giving you guys that time to work on the exam. So keep that in mind. So I'm gonna have like no late submissions at all. So 9 o'clock is the hard deadline. That's why I say just get it in, do it as soon as possible so you don't have to worry about it. Okay, and I'm gonna have the exam is going. I'll put up on Blackboard the exam and everything, but basically it's going to be an overleaf template, and just like a lot of classes have done, where you just fill in the blanks. So in terms of you enter the question, just write your answer in there. Okay, and then you'll submit the PDF on Blackboard. All right, I don't need source code. I don't need anything like that, just a PDF. I will know that you did it because your name will be hard-coded in will be hard-coded, so I know that at least you did it. Okay. Okay, so as a matter of review, there are some resources for the midterm. So I have a number of papers that are basically have to do with the course content we've been talking about. So we were talking about particle systems. We were talking about flux. So like particle choreography. How do you get these things to work together? How do you go about animating them, rendering them? We talked about like simulation loops and so on. Right now we're kind of in the midst of doing fire. So these are the papers we're going to be kind of looking at today: depicting fire and other gaseous phenomenon, particle-based fluid simulation for interactive applications, stable fluids, and visual simulation of smoke. This last one has just got some more detail on SPH if you're more interested in it. This is a big document. I am not digging to like page 40 something to find something to ask you about. Generally what I'm trying to get is, do you understand the material and do you know where some of the major contributions are in the field? Okay, so as a matter of review, I'm going to switch over to this one over here, because that actually is okay. Right. So more or less, we started talking about what are some of the basics when it comes to simulation. So we were talking about like the simulation loop. Let me close this stuff here. Oh, new insider. Okay. We talked about collisions, whether there's 3 steps. There's the detection part, then determination, where it happened, response, what do you do once you know it happened. Then we have particle systems. So a lot of that's, how do you go about generating random numbers? How do you generate where the particles are coming from, the actual particles themselves, the vectors, where are they heading off, what direction are they going? The generators, which are mainly responsible for, you might have different kinds of generators depending, and they might have different shapes. Okay, so a fireworks simulation or generator might look different than a water spout, or like a stream of water or something. Okay, and then how do you take these particle systems and then go about rendering them? Okay, and that kind of goes along if you just look at Reeves' original paper on a technique for modeling a class of fuzzy objects. Okay, so how do you go about representing that? Okay, then we started moving on to, so that's some of the basics of particle systems, and we started going into choreography, like how do you do stuff with them. And this is kind of where whereas you kind of look at before, there's not a whole lot of physical based stuff going on here. There is some, but if you look over here, then we're getting into operators, and you have acceleration operators like gravity. You could have some non-physically based operators as well, like velocity operators. Maybe you're trying to get particles up to a minimum velocity. Maybe you're trying to get them to make sure they don't go too fast. You might have maximum velocity. Those are not technically physically based. Yes?
Would a bounding box effectively be a position operator?
Yes.
Okay.
Yeah. So, although it's more, a lot of times, so we might call that like a boundary condition, rather than an operator.
Suppose like position operator would depend on whether or not you're actually just like keeping the positions and they run up against the wall, or you're actually like doing something with the velocity, like bouncing them off.
Right. So, and that might be part of the collision response, if you're handling that. So, I don't know that the book is using the term position operator, but a lot of times it's actually more beneficial for you to think of it as a boundary condition. Especially as we're talking about fluids, because that whole term, will help you understand the differential equations, partial differential equations, where the boundary conditions help keep everything in control. Okay. All right. So then we started talking a little bit about spatial data structures. Spatial data structures are useful when you have lots of particles and you need to get this under control, because sometimes it's just like collision. If you're trying to have every particle interact with every other particle, then it can quickly go be something you cannot calculate, especially if you're doing an interactive application. So because of that, you may want to, like the galaxy simulation. Erase this. So, you might have, you're simulating a galaxy, right? And you might have like the core, and then you might have an arm, you might have another arm, okay? And then you might have like pockets of gas or something that you're trying to do. So an acceleration or a spatial data structure, maybe what you want to do is divide up the problem so that you can say, here's what's happening with all the particles in this area, and we can kind of, then we can use this data structure to say, as a whole, here's how all the particles are working. This is the total mass, this is the total rotational or angular momentum, this is the total momentum of this one. And then what you can do is then every one of these particles not interacting with these individual ones, they're interacting with this giant block of them. Okay, so that reduces your computational complexity by subdividing it using that spatial data structure. Okay, and then flocking, what kinds of rules can you come up with to have your particles interacting with each other? Okay, it could be, you might be trying to simulate animal behavior. It could be crowds. Crowds are very, very popular. Anybody watched a movie that didn't have crowds? AAAs are like Lord of the Rings, right? You're not going to get that many people or that many creatures and puppets, out and looking that good. Okay, so you use a lot of times this stuff is used to, how do you get lots of actors? What was the term that was used for an actor in the flocking paper? Poids, yeah. So. Okay, so now we're done with particle choreography. We're starting to move into fluids, and yes.
I was just going to check, especially the spatial data structures. Is there a specific lecture section that was posted in, or is that mainly in the Hybrid Topics video?
We talked about. I don't know that we talked as deeply about spatial data structures in class. But we may have, let's see here. maybe one of these papers may be loosely talking about it. I think we just talked a little bit more general about it in the class. We didn't jump into too much detail, but
how specific will we need to like understand it, or like some like the specific models for the exam? Just going to be mainly understanding like how they're used in general, or
yeah, I think it's how they're used in general. So what you should do if you're going to talk about a spatial data structure is you should cite something. Talk about, because I might ask a general question. How would you go about simulating a galaxy, right? And so you would need to talk about that. But maybe there's a specific technique you're thinking about, or I don't 100% remember if one of these papers I selected specifically. Let's look at the 1983 one, because I feel like it would be more needed in 1983, given the classes of computers out there. And then for all these papers, if you have, most of the time you can just search for these on Google Scholar and get to them. But if there's a paper that you're having difficulty getting to, then please email me and I'll post it up on the Slack board. Okay. Spatial aliasing. So not really in that one. Carl Sims might have talked about it. I'll put it this way. If I ask something about it, I'm going to have a paper talking about it. Okay, so because I don't want you guys to just be study for everything, but as a matter of review, I just want you to be aware of it, and it's in the notes, right? The spatial data structures and stuff. Okay, so I'm not going to get too much detail right now because we do want to spend most of the time on the fluids part. Okay, so we're going from particle choreography, and I noticed that we're dealing with the particles, especially in our visual simulations, and they do have like a way of interacting with, especially when you turn on the collision detection. They almost seem to act like fluids in a way, especially the way they bounce around. Although we're not specifically modeling that kind of behavior, but there is some element of it, in terms of how they're interacting, right? So that kind of gets us into some of the mathematical foundations of fluid simulation. We have this concept of Lagrangian versus Eulerian, and does anybody tell me what the main difference between the two might be?
Continuous versus discrete, was it?
that wasn't a grid.
Yeah, one's on a grid, one's particles. One could be considered continuous, one could be considered discrete. Obviously the grid doesn't move, so you have to like sample it in a discrete kind of way. One's more particles. So we've been applying a Lagrangian approach to our simulations, just simply because they can move anywhere they want to. They might have fixed mass and so on and so forth. And then, the Eulerian approach is we might use a discrete grid to do the simulation on. We talked about, or at least I introduced the differential operators, okay? And this is where the math gets heavy. We lay it on thick, right? Extra crunchy peanut butter, it can be a lot to just like, when you're coming from a calculus background, which many of you guys, that's probably where it stops. All of a sudden seeing mathematical operators who, it almost seems like their entire purpose is just to make more math for you to solve. In terms of, like for instance, there are some operations you can do on a scalar field that turns into a vector field. So now you just multiplied all the numbers that have to happen, okay? So we have 4 differential operators. What are the 4 operators?
Gradients.
Gradients, yeah. That's probably the easiest one to do, gradients. What's the next one?
Curl.
Curl, yeah. Divergence, okay, yeah. And the last one. It's named after a guy. Hopefully that helps.
For the Laplacian.
The Laplacian, yeah. I call it Laplacian. It could be Laplacian. It's probably variations in how it's spelled, but there's 4 differential operators. Okay, what is the gradient for? What do we use the gradient? What does that tell us?
Rate of change or flow, basically.
Sure. Rate of change of flow.
Discrete system, for instance.
What else might it tell us?
It's basically a slope-like structure, isn't it?
Yeah, it's like the derivative. It's like taking the derivative on a 2-dimensional function. So, you know, if you have y of x, it's like taking the derivative. Okay. Divergence. What is divergence like?
The one that sort of represents sources and sinks. How do you identify them?
Not exactly. In fact, some of these we're actually trying to like shove off if we can. Just kick that thing off the table because we don't want to deal with it. But I think we're going in the right direction, right? With derivatives kind of relate. I mean, we have the gradient. It's kind of related to derivative. Divergence is kind of related to, what do you think? It's kind of like integration. It's kind of like integration. And then we have the curl. What's curl like? It almost defines itself. It's kind of like cross product. Okay. It has to do with rotation though. Like angular momentum would be defined like curl. Okay. How is something turning? The example that I gave was if you can imagine, you know, a stream, you might have like an object on there spinning. That would be like the curl. So if you've ever, you know, been on a river or seen something, or just take a little ball that can float or a little rubber ducky, and just spin it in your sink or in a bath, and that's the curl happening. Okay, that's curl. Okay, and then lastly, the Laplacian. We're not going to go there because that one's too hard to think about. Okay, the Laplacian.
It's the divergence and the gradient.
It's
That was informative.
yeah. It's like a double integral. It's how is maybe one way to think about it is how is the gradient changing? Okay, how is the gradient changing? Because it is. It's like the dot product of so it's the divergence of the gradient. The divergence of the gradient. Divergence. Now this one is now it is kind of related to the sink and the, you know, so I will give that to you. It more or less kind of defines the how the velocity is changing, like the flux. Okay, and so generally though with fluids, or the kinds of fluids we're looking at, we want it to be divergence free. We don't want the divergence of the velocity. We want that to be 0. Okay, so that's one of our preconditions that we're, you know, to help make things more simple. Okay. All right. And then we were talking about potential field flows. Potential field flows. Now, I think the potential field flows is kind of cool because it's more or less how are we trying to change it so that it's something we can handle. All right, so let me open up a preview of this one. So week 7 has a lot of good notes in it in terms of what I copied from the book. Okay, but here's what we can do with it. Okay, so first of all, let's put our Navier-Stokes equation on the board. Although I think it's kind of funny. Does anybody know what Navier and Stokes did essentially? No. They took Euler's equation. So if I go here, Navier-Stokes. They took Euler's equation and they basically generalized it. Okay, so you have Claude Louis Navier and George Gabriel Stokes, and the idea is that they wanted to understand how viscosity affects fluids. Okay, so and if you don't think it's a hard problem, okay, the Clay Mathematics Institute called this one of the 7 most important open problems of mathematics and has offered a $1 million prize for a solution or a counterexample. Okay, so if you guys saw the little meme in there, one does not simply solve the Navier-Stokes equation. That's kind of like, I mean, it's like, oh yeah, that doesn't look so bad. It's like the Renering equation, but I tell you what, the Renering equation is a far easier thing to solve than the Navier-Stokes thing is. Okay, but that's fine because now we're jumping in on the really hard problems. Okay, so let's go over here. So derivation. So the idea here with the Navier-Stokes equation, and I need to find Euler's fluid. If you don't know very much about Leonhard Euler, that guy is an amazing character. Amazing character. There's like, I feel like his name is over on everything.
List of topics named after. Nice.
I mean, this guy was brilliant. He even had a brilliant face. Okay, things that he helped solve. Okay, so pumps, turbines, defining rotations, rigid bodies, helping us solve certain numbers of ordinary differential equations, partial differential equations, so fluid dynamics, Euler's formula, there you go, relating E to the cosine and the sine functions, the complex plane. This is something that you really couldn't understand electromagnetic waves without this particular equation. I mean, it's that important. There was the famous 7 cities problem, where could you design a tour that you couldn't cross through the 7 bridges? Yeah, the 7 bridges problem. So he made contributions to graph theory, loads of a column. What else? Some Euler functions, identities, Euler's number, E. Every time you use E, that's named after him. The guy was brilliant. Brilliant. And he lived, normal life. Yeah. Yeah, 76 years. Pretty good. Yeah, this is this guy was amazing. So if you're ever looking for a character to read, Leonhard Euler is quite the character. Okay. So anyways, so there's Euler, the Euler equations. All right, and so as I was searching for or studying the Navier-Stokes equations to kind of understand, because a lot of times you just hear Navier-Stokes, and that's how you like talk about fluids. And then I was looking at the Euler equations, and more or less, as we're talking about simplifying the Navier-Stokes equation, we're basically working our way back just to the Euler equation. So in fact, really, in this class, while we are working with the Navier-Stokes equation, we are really, for all intents and purposes, only focusing on the part that Euler was working on. Okay, so in other words, getting rid of the viscosity, essentially. Okay, so yeah, because this is so the incompressible, right? You have du dt equals minus the gradient of w plus g, and the divergence of the velocity field is 0. Okay, and I think that's it. Okay, so there and right there, this is the so the gradient of w. You have pressure over the density. All right, so 1 over the density times the gradient with respect to pressure. So if we go over here and we look at this equation here, we can see. Let me move my mouse. We can see that this is basically Euler's equation. The only difference is this viscosity term. Okay, so and if we look down here towards the potential field flows, that if somehow we can get the gradient, where is it? Irrotational inviscid, right? So if we can get rid of the turbulence part, in other words, get rid of this term up here, if we can get rid of the turbulence, then basically we're just left with the Euler equation. Okay, so I thought that was funny. I thought I would share that with you. That we're talking about all this time. We're going to solve the Navier-Stokes equations, but essentially we try to make the part that Navier and Stokes really added to this equation. So they more or less generalized the whole thing. Okay. And we were looking at turbulence, right? So inviscid. So maybe we could find I guess turbulent water would be what happens with white water. Now, I mean, if you think about it, when you add turbulence to your simulation, what do you think is going to happen?
Sounds like it's going to get messy fast.
It's going to be messy fast.
With the hips.
Okay.
All your swirls, all your fun little. I mean, it'll be interesting.
Well, the funny thing though is that the swirls don't necessarily need to involve turbulence. Okay. Yeah, and that's another thing. Like if you have water crashing, if you look at the ocean and the water crashes and it creates a bunch of foam, that changes the turbulence or the viscosity of the water, and it fundamentally changes the whole equation. Well, it doesn't change the equation, but it changes the dynamics of the equation, the way it works, and it's very easy to. Let's see here. I am trying to find.
What do you need to do to have cavitation?
Well, there's a certain phenomenon that happens with fluids, and I'm trying to remember. It's called it's like a walk, and I'm going to end up causing my computer to. Has to do with the My book's in my office, and I just forgot the term. There's an L word. It's kind of like when you're driving down the road. This is something you can relate to in Alaska, and there's snow blowing on the road, and it creates those swirling patterns on the road. It's really hard to describe to anybody who doesn't live in, I guess, a snowy area.
With the vortices.
Yeah, they look like vortices. But it occurred to me as I was driving that they're creating vortices, but what's happening? It's really just the velocity of the air, and it's creating these. It's kind of like a laminar walk or something like that. The term walk. That's right. Reynolds. Maybe I could type in laminar. Oh, I don't want the picture.
I saw it.
There's a specific name. Let's look at this one.
So what's the phenomenon though? So there's a laminar flow, and then there's like vortices trailing behind it or something?
Yeah, it has to do with it's not something though that you need to. So there's turbulence, but there is an effect. You have what's something, I know you have something that's called a Reynolds number, and more or less this tells you when it's going to transition. There we go. A vortex street. I had it in my head walk. A vortex street. And I was thinking to myself as I'm walking, as I'm driving, you know what? Now that I've been studying this, I'm like, that's what's happening. Is you have this vortex street happening because they are. If you're like watching the patterns, like they are kind of have that pattern, because it's just kind of caused by the, your car's driving over the surface of the road, and you have that velocity change of the air on the top, and the air on the bottom is not doing anything, and so, you end up creating these cycles, and they happen the Kármán vortex street.
Actually, yeah, no, I've totally seen that. It's actually been one of those things I've been like, why does it do that?
Yeah.
I've been educated.
Okay. Kármán Vortex Street.
It's the same thing when you like put an ore in the water.
Yeah, I think that's the same. That's the same thing that's happening.
So that's it.
Okay. Now, the thing is that you don't necessarily have to have, if I'm correct, the vortex street. You don't necessarily have to have, you don't necessarily have turbulence to create that. And that's the thing I was like, oh, that's interesting. So you can still have this effect show up. You can still have this effect show up. But it doesn't necessarily have to I think it's because it turns out to be a constant. It's just what happens. Okay. Anyways, so getting back to here. Okay. So no turbulence. All right. Although I'm pretty sure you can still get those vortex streets without the turbulence. And let's see if there's... $1975. Okay. Okay, so this might be something to we might have looked that up at some point. Okay, let me see if anybody's... Because there are some nice little simulations on here. I'm kind of working on one so it's a little easier to understand, but just haven't had time to do that. That doesn't look like it's real. Sometimes things look too good. Oops. Banging around here. So let me go to Chrome real quick. Close window. Sign in. I don't know if I forked one of these things off or not. I don't think I have yet. Oh, I gotta click on my name. I think I was working on, I'm starting to work on some stuff like like the torch fire. I kind of recreated my torch fire inside of Shader Toy. I guess it's running a little slowly right now, but more or less it's just using that advection type where you just blur more or less. It's like a little kernel that blurs. So it's like, okay, and then more or less you can get a torch fire out of it. So I'm working on some demos to kind of help illustrate some of those fluid principles. But yeah, so anyways, we got the Navier-Stokes equations up there, and we're like, how do we make this simple for us to actually work with them? And so one of them is, well, let's just make some assumptions, okay? So number one assumption is, let's make it steady. So in other words, rather than have it vary in time, we just say it doesn't change in time. Okay. That doesn't mean it's not evolving over time. It just means that that our velocity is not a function of time. So that's one way of making these things more simple. Secondly, we can say it's inviscid, so there's no turbulence. So we'll just model it. I guess more from a macro scale, there could be turbulence, but we're not saying there's internal turbulence for each of our elements. Okay. Then incompressible. In other words, imagine who watched at least some of the MIT video where they talk about the compressible fluids, the gas. I thought that was really neat because sometimes we throw things out like, okay, what does it mean for something to be incompressible, and what if it was compressible? And so the one thing I liked about the MIT video was that you could see what happens when you allow it to be compressible, that you get all these strange effects that happen, like the shock waves and all that kind of behavior, things like that. I mean, I was just trying to imagine if I was doing a visual simulation of that, of what I saw in the MIT video, what do I think, or what would I think if I saw behavior like that? In other words, when numbers decide to just jump like crazy and do, I would probably be like, I don't know how to maintain a simulation like this. Now, in real life, you have, uncountable numbers of atoms interacting with each other, right? And that's why more or less the behavior happens naturally. But inevitably what happens when you start approximating things, you start to lose the fine detail that happens in those types of situations. And then we like to use the term blow up. Your simulation just blows up on you, and it just it turns into a giant mess. You can't recover from it, right? You might have because some parts of the simulation, right, are acting politely, and then there's some parts that are just like, we have no way of knowing what's happening there. Technically, we're not able to calculate numerically what's happening. Okay, so incompressible. And then irrotational. In other words, we say the curl's always zero. We don't have any support for particles, essentially, that have their own rotation built into them. So when we're thinking about this, like with Lagrangian or Lorentz, and we're thinking about this, okay, irrotational, right? Because if our particles, if it supported rotation, our particles we'd have to support some amount of spin to them if we're going to have that phenomenon show up. That's just going to have to be part of it. Same thing for the Lorentz, although it's a little bit harder to imagine. If you have a grid, right? In a way, it can be kind of hard to imagine to some degree that having some spin associated with it, but it does. Okay, so we might want to say that it's irrotational. Okay, and so what this is nice though, because if it is irrotational, then it means that our velocity field can actually be turned into a scalar field. Okay, so we use which Greek letter we use to represent a scalar field?
Rho.
Not rho. Rho is what do we use rho for? We have lots of things that look like peas. Rho is one of them. What is rho used for? Density. Yes, density. So we use rho for density. We use phi for scalar field. And what do we use to represent vector fields? U. We use U. Okay? So, the reason why we're doing that is so that as we're looking at all these equations, we're not, so we're also using bold letters to represent the vector fields, but we're using U to represent the vector fields, and we're using phi to represent the scalar field. Okay, and so just as a matter, so when you look at the equations and you're thinking to yourself, you're thinking, okay, what are each of these things doing, right? So we have a vector equals, we've got U dot gradient times U. We have. So what do you think is going to happen over here when we take the gradient of the pressure field? What's that going to turn into? It's going to turn into a vector field.
The gradient of pressure
It's going to turn into a vector field.
like pointing in the direction where like the high pressure, the low pressure is.
Right. So the changing pressure is going to cause a change in velocity. Okay. So some of these differential operators will cause our equation to, you're like thinking, okay, I have a bunch of, I have a bunch of just these random numbers over here. Okay. So you have a scalar field. You take the gradient of that, and now you've turned it into a vector field. Here's why that is. Here's why that is. So let's just say the Eulerian method. Okay? And let's just take this cell right here. So we have the x direction, say it's 3 minus 5. In the y direction, we have, on this side, we'll call it x1. And then x2 will be 8 minus 7. And then over here on the y, we'll have y1 equals, say, 7 minus 3. And y2 equals 8 minus 3. And then we gotta combine this in such a way, but you see that the pressure, we have an x component, and now we have a y component as well. So now we've taken something that is just a single number and turn it into a vector. Okay, so so we take the gradient of a scalar field, and now we have a vector field. Okay, and then if we take the Laplacian of a vector field, we will get a what out? Once again, you can use the context of the equation to tell you what's going to happen. We know we're getting, this whole thing is a vector. So if we take the Laplacian of a vector field, we're going to get a vector field out, because we can't, think of it like units, right? You can't just add meters and time together. It's not going to work out for you. Okay, but if there's a way for you to convert time into meters through some operation, then now you can. All right, so same idea here. So we take the gradient of the pressure field, we're going to get a vector field out. We take the Laplacian of the vector field, u, and now we're going to, which is the velocity. So we take the Laplacian of the vector field, and we also get another vector field out. If we, now this irrotational one, if we happen to take the, so if we set the curl to 0, so there's no curl, there's no rotational component, then we end up basically turning the velocity into a scalar field. Okay, but mostly what that means is that we're going to end up getting rid of that viscosity term. Okay, that's what's going to end up happening. And then G, what does G represent? It could be gravity, yeah. It's our external acceleration. Okay, and in many cases, gravity could be a component to this whole thing. Okay, so So we're making some assumptions about flows. Here's what we can do. So we can say that it's steady. In other words, our velocity field doesn't change with respect to time. It's inviscid. There's no turbulence. It's incompressible. So our, which is normally something we want anyways. And then irrotational means that there's no rotational element. And so what that will allow us to do is turn the velocity into a scalar field. And as a result of that, if we take the Laplacian of that scalar field, then we end up getting 0. All right. So now we have basically just turned into an Eulerian fluid. That's what this is all saying. Now, here's what we can do. Because of this, there's 3 effects that we can cause to happen. The first one is we can model uniform flow. Uniform flow. And the way that we do that is if you imagine a vector field, what do we think uniform flow is going to look like?
They all point the same way.
All point the same direction. They're all going in the same direction. Okay? So that's kind of boring though, right? I think that's boring. But it's useful though because you might want to have some parts that are uniform. Like you might have an initial condition where maybe you have like maybe these 2 ones have uniform flow just to get it started. All right. The second one, and we can see over here that that then the gradient of our velocity field is then just the A, B, and C components. Okay? Because the derivative with respect to x is A, the derivative with respect to y is B, and the derivative with respect to z is C. So then our gradient of our scalar field is an ABC. All right? Now, sources and sinks. So we might actually want to have some components where this is where flow is coming out of. Or it kind of acts like a repulsive force, right? We want to move the water around. This could be like turning the faucet on. Okay? It could be like turning the faucet on. And similarly, we might want to have a sink. In other words, let me just add some more dots here. We might want to have a sink where the flow is going towards. Okay? So we might want to have a sink. So this is this would be a source, and this would be a sink. And so they look very close to each other. So we have that it's basically defined phi equals a over 2 pi times the natural log of r. In other words, r is the distance from that point. So we would say that more or less, if you had a sink, then all these things are kind of pointing towards a sink. But it's based off how far away it is from that sink. Okay? So then if you take the gradient, you take the derivative with respect to x, and you end up getting v over a pi r. And I'm not going to work on the derivation there. And the other ones are zeros. So depending on what you set A and B, that'll define whether or not it's a sink or a source. Okay, so basically one you're kind of defining it to be positive, the other one's negative. So it tracks it or opposes it. And then lastly, we mentioned that we're not doing any inviscid fluids, no turbulence. However, we can have vortices. And so the way that a vortice might work, that's more points here, is that maybe this is a vortex, and that means we'll set our the angle as the so instead of using the distance, we're going to use the angle, so v over 2 pi, and then you take the derivative and you'll end up getting e over 2 pi r. The book kind of goes into some derivation, and I want to put some examples together to kind of show how we use these. But what ends up happening is that this one would end up going this way, this one ends up going this way, this one ends up going this way, this one ends up going this way. And the distance r basically affects how wide of an effect, or it's like a field effect, right? Kind of like our acceleration operators in a way. It just kind of depends how far away you are. This one would be pointing this way. So in essence, what you're doing is you're creating this movement inside the fluid. And so what you can do with these is you can overlay them on top of each other and essentially simulate all these different kinds of effects. So as an artist, right, you might be putting together this animation together and you say, okay, here's my Euler, maybe it's an Eulerian simulation, and you say, okay, over here I'm putting a uniform flow, and over here I'm putting a sink or a source. Over here I'm putting a vortex, and then let's see how the whole thing evolves over time. So without needing to kind of get into the whole turbulence aspect of it, you can basically simulate a lot of these effects. Easy? Okay. I like to chuckle because it's not.
Well, I can tell a computer to do all the work for me.
Well, that's what we're trying to do, right? Now, I'm thinking that maybe I try to compress. I try to take an incompressible subject and turn it compressible. So I do want us to be successful with this. So we're going to spend some time trying for everybody to be able to successfully make a fluid, okay? Because unless you don't want to, who doesn't want to simulate a fluid by the time they're done with this class?
Kind of project I have, so I better do it.
Okay, you want to. Okay, who doesn't want to? They're so opposed that they want to leave this class and never simulate a fluid. Okay, so so we have some different methods, right? Okay, so we're kind of going over Lagrangian versus Eulerian. We kind of spent maybe a little bit of time talking about Eulerian. Okay, we're going to talk about Lagrangian. We kind of reviewed a little bit of the mathematical background, the Navier-Stokes equations to some degree. We basically just decided that for a good deal of what we're trying to do, we're just trying to do an Eulerian simulation. Okay, or an Eulerian. This is where it gets all. Maybe this is why Navier-Stokes is so popular, because then we don't have to say the Euler equations when we're talking about Eulerian approach and so on. Okay. The other thing we used his integration method at the beginning of class. Remember, where we time stepped it. So yeah, he's like all over this class. His fingers are all over this class. Okay. We're talking about potential field flows over here. So how do you get your simulation to more or less kind of act certain ways? And so I think that's cool. So one way to do, and we're going to not actually go in this order, but I wanted to talk about the smooth particle hydrodynamics, okay, which is a Lagrangian approach. All right, Lagrangian approach. Does anybody have any questions? How many people watched the SPH video? Yes. That guy's cool. Okay, so I thought, hey, what better way we could learn from the guy who practically invented the method to begin with to talk about it. Who knows one of the most defining aspect of it, or what popped out the most? Okay. So I would say the most defining aspect of the whole thing is that weighting kernel. The weighting kernel. So How many people feel like they have a really good understanding of the Lagrangian approach? That's all we've done in the class is Lagrangian. The particle simulation that we have is all Lagrangian. Okay. So we've all worked with the Lagrangian. We have particles that are all independent. They can be wherever they want to be. It's all Lagrangian. Okay. Because at this point, we have not stuck anything inside of the grid to do anything with it. Okay, our particles can do whatever they want to do. So smooth particle hydrodynamics is a Lagrangian approach. Now, let me find an image. Maybe let me go to our Mueller and others is the paper where they really talk about SPH. Okay. And oops, this is probably a really good paper. Well, they're all good papers. I didn't pick bad papers. So their thing was, hey, let's pour glass into a water. All right, let's pour water into a glass.
That's slightly different.
Slightly different exercise. Okay, and so I want to find an image where this is Lagrangian. This is why it's a Lagrangian approach. So we're watching the fluid, but this is what's happening. Okay, imagine a whole bunch of marbles inside of a glass, and the Lagrangian approach to this whole problem is, let's just simulate a bunch of particles. Now, I hope that you're thinking back to the collision detection, when we're talking about collision detection, because you can see that this is going to be a fundamental component, right? You can't have particles passing through each other. Why can we not have particles passing through each other?
Well, make it fluid compressible.
They make it compressible, okay? Each one of those particles represents a constant amount of mass and a constant amount of volume, right? We can't, so what is going to be the immediate issue with trying to do this approach?
Like, there's going to be a lot of complexity in just having to have them all interact with each other. I mean, it's a collision problem. You're going to limit yourself.
N squared, right. So you got to think about that, okay? Now the collision part, you're like, okay, if you were trying to solve this collision problem, what would you do?
Would be the dumbest way.
Yeah, but would you though? Would you?
I mean, so the thing is that the particles shouldn't magically teleport to the other side of the fluid. Like they're generally going to be sticky and viscous, and there's going to be some friction. So they're generally only going to interact with things nearby. You might be able to do some sort of blocking or neighbors technique to try and say, you've interacted with these guys before, they're close by, they're the first things you should think about.
Yes.
And try and limit it that way.
Yes.
I don't know how you would do it, but you could probably try and make a priority list, so to speak. So some parts are close, you can check collisions with them. Although I would still be checking collisions with all the others.
Yeah, because but what if splashing or something? There is possibility of it going across the simulation space. So I feel like even if you did a neighborhood calculation, you'd have to do it every frame to update neighborhoods, right?
But the thing is the neighborhoods can be updated in linear time most of the time.
Yeah.
Sure.
Once you get linear
split
plus
into some grid, I get you.
Yeah. I mean, it's still technically like a sort of n squared thing, but it's n squared divided by something, which, well, in big O terms is not important. It doesn't matter for practical use.
Okay. So to some degree, we have a collision detection problem, which we can just bucket things together, right? So in real life, if we were just modeling all of these particles inside of a volume, we do some bucket approach where we subdivide the area and we only do collision detection against the ones that are close by, right? Okay. I want you to have that in your head because that's one part of the problem, right? We're simulating collision detection between the particles. That's not the only thing we have to do between the particles. We have to simulate the fluid aspect of the particles. Okay. In other words, and this hopefully this makes sense. But if we had like a smooth fluid here, like this volume of fluid, and I tap on the glass. Let's just say this is, and I tap on the glass here. What happens over here? Ripple, right? It would eventually spread across the entire thing, right? So just this is the issue where now the collision detection, you can say, let's look at this local area, right? And just do collision detection around there. But now all of a sudden as a fluid, if I tap right over here, then this is going to have some kind of effect, right?
It would be able to pass.
Because every particle depends, ultimately, this is like a giant set of partial differential equations, and they're all interconnected with each other, okay?
Elastic collisions, or inelastic, depending on whatever precise
Yeah.
you want to handle.
So here's what we do. I mean, if you're thinking that we're going to try and, we also need to model the Navier-Stokes equation with the particle, from particle to particle, okay? The question is, well, which particles do you do that with?
The ones that are touchable.
Theoretically, you could do it with all of them, right? However, the key to this approach is that we use this weighting approach. Okay, in other words, that the contribution, okay, so we have particle I and particle J, all right? So let's look over here at this equation. So we have all the other particles. So we have the mass of those particles times the field quantity divided by the density of particle J times this function W. That's the smoothing kernel. And the whole point of the smoothing kernel is to say, what is the contribution of particle J with respect to particle I? Just like the collision detection problem, where we'd say, does particle I collide with particle J? Same idea here. Now here's what we do with, and this is why it's called smoothed particle. We use this function, it's a kernel, and we say that one particle will have an effect on another particle if it's within a certain distance of each other. And not just that it's within a certain distance of each other, but that the weight that that particle has on this other one is dependent on some other function. So if it's closer, we would expect it to have more influence, and as it moves away, we would expect to have less and less influence. Okay? All right.
So, the other one's too far away.
Well, here's what we can do. Okay? We can say, essentially, we're going to use a whole bunch of particles. So we'll call that spatial sampling and reconstruction. In other words, we want to divide our volume into a bunch of particles. Later on, we want to reconstruct it so that we can say what the fluid looks like. But for now, the mass of particle I equals the density at that point x times the volume, right? Mass equals density times volume. That's going to be important later. So then we want to estimate pressure by considering all the nearby particles. So if there's a lot of particles, there should be a lot of pressure. And if there's not so many particles, there shouldn't be a lot of pressure. So we have this distance. So this is our weighting. This is our smoothing kernel, W. So sometimes you'll see capital W, sometimes you'll see lowercase w. It just amounts to a weight, essentially. And so we might want to say that the maximum support is, and we talked about the idea of a support function when we talked about collision protection, where it's almost like a sign distance function, where if you're, it kind of tells you how close you are. So like a support as in, like I'm supporting this. Okay, a support function. In other words, how much does this particle rely on the support given by another one? So we might want to say that at a certain point, that if we're a certain radius r max away, that it's 0. So in other words, we don't. This is how we're just like the collision detection. We say let's only consider nearby particles. Like if we can bucket it somehow, then we can kind of improve the efficiency. Same idea with the smoothing kernel. We want to say, let's take only some particles. And after a certain point, then there's no more of them. Now, it is important that we normalize the kernel. So if we were to take the integral of basically the volume that represents, then it should equal 1. Okay, so now we have field values, all right, phi of x. So this is how we're going to start calculating. This is how we're going to start calculating things like pressure and stuff. They're going to have like this very similar nature to them. So we might have that, and then notice how we have the mass and the rho, the density here. So that tells you that if you think about this, right, that this is that this piece here more or less represents the volume. Okay, you see that relationship in there? So these equations have the concept of volume inside of them because we're dividing out by the density. Okay, so the question is, does density remain constant?
Why wouldn't it?
It's kind of a trick question, and the answer is no. This allows us to have variable density, right? Because what happens? I mean, let's take a look at these particles and these particles. Which one's more dense? Yeah. Okay, so one of the tricks here is that we can allow density to fluctuate. Okay? Because, and more or less, the key to think about is that represents volume. Because volume equals mass divided by density. Okay?
So, technically speaking, that means the fluid, like, it's incompressible past a given point, but, like, if there was a point where the density was down, it means it could be compressed a little, right?
Yeah, in a way, you can think of that. You can compress the particles together, but at a certain point, the individual particles themselves cannot become compressed. So technically, the particles are not compressible, and that means that it's not compressible. Okay?
But the collective is.
Okay. Particles carry their own mass. All right? That has to do with, remember we were talking about convection and advection, or I mentioned it. Okay, mass is a property of fluid. In other words, it's not like it just changes on you. Okay, the mass. So if you were to mix two different kinds like oil and water together, they don't mix, right? Of course, we know they don't mix. Okay, so there's no way that the water is like some part oil and some part water. Okay, they just don't mix. So that's what that means. Particles carry their own mass. Mass is a property that can be moved along. So if you can imagine, if you swirl a cup that had oil and water in it, the oil would move around and it doesn't become separate. It's just part of it. Okay, so they have their own mass. So at each time step, then, we have to start calculating a few things. So we have the Navier-Stokes equations up here. first thing we need to calculate is the pressure gradient. Second thing we need to calculate is the velocity and the velocity field. And lastly, the external applied acceleration. So in this case, because we're doing SPH, you'll notice that we're not just discarding the viscosity component, right? We might want to. We saw that we could do some very complex behavior just by throwing that term out over here. But now we're moving on to a different way of solving the fluid equations. Okay, we can keep the viscosity in there. So part one is the pressure gradient. And I apologize because sometimes it's hard to control what the math is going to look like in the PowerPoint. But let me switch over here real quick. This looks a little bit better. Okay, so in order for us to calculate the pressure gradient, then we can, and I don't have any derivation for us here. I just kind of use the bottom line up front. Okay, this is more or less what we're trying to calculate, the pressure gradient. And the way that we would go about calculating it is we would just take all the particles all the nearby particles, right? And those get multiplied. So you take the mass times the pressure from particle I divided by the density there, plus the pressure of particle J divided by the density squared, times the gradient of the weighting function. All right? And then the second term on the Navier-Stokes equation has to be the diffusion term. And just like, so we take this part, and in order to approximate that, we could say, take the velocity of particle J minus the velocity of particle I divided by the density of particle I, and then multiply by the Laplacian of the weighting function.
Is this weighting function constant according to the method, or do we decide on that?
So we're actually going to talk about that. Okay. That's the next part. Okay, so we actually have some pretty straightforward equations. I'm actually going to get you to try it out myself.
Gotcha.
Okay. The equations, though, it's like, oh, okay, so the pressure doesn't look so bad, and the diffusion term doesn't look so bad. So, and then the external acceleration, just as a question, what can we use that for? Yeah.
Any external acceleration, gravity.
Gravity.
We could be completely insane and do charges or something weird.
This is like your ability to. We're already doing this, but this is like your artistic control. You can say, I'm gonna put some kind of like effect inside the fluid to do something. Maybe I want something to stir it up or something. But how easy is it for us to apply acceleration to particles? We've been doing that. That's the easy part. In a way, it's like we're adding some extra acceleration operators based on pressure and diffusion. Okay, that I think is cool. Let's take a look at the kernel. I'm probably saying his name wrong. I'm going to say Monaghan.
It's Monahan.
Monahan. 1992. Came up with a spline-based kernel. This guy, like I said, really pushed, I mean, his name is all over this particular method. So he created this spline-based curve. And we have a way to calculate essentially the gradient and the Laplacian of this smoothing kernel. So the trick is, let's take the hard part of the problem, like these Laplacians and gradients and so on, and let's find a better way of doing it. If I'm correct, the paper here has graphs of, here's some smoothing kernels. Okay, so the thick lines show the kernels. So and if I can make this bigger, I'm going to try and make it bigger. Fill up the screen. So this is a smoothing kernel. So you notice how we almost make it look like a Gaussian, where over here it has zero effect. So if you're a certain distance away, no effect at all. And then we can take the derivative of that. So the gradient looks like this, where it goes. All right? And then we'll Laplacian it as this. Those are the dashed lines for Laplacian. And that's how we use our. So basically, that's some polynomials we can use for our fluid. Not bad, huh?
Just get lost in the math symbols. But once you just show, like, this is how they're calculated, I'm like, okay, cool, got it. I lose whatever.
There's a point where I regress to, okay, show me some code doing it.
Right.
Show me how changing something in the code changes what's going on. Okay, cool, I get it.
And I totally understand, because even for me, it can be hard to translate. Now, I think I've spent enough time diving in the math that I have a feel for what these things do now, and it's like, oh, okay. And especially if you can take things like the collision detection and kind of think, oh, it's just acting like that. And when you see what's happening, it makes a difference. Okay, so I did want to talk. So there's the smoothing kernel again, but I did want to talk a little bit about. We'll talk real quick. How do you make the surface, right? Because we already mentioned, like in the paper, this is what it looks like. So, okay, so we have a bunch of particles. Now, how do you make it look like a fluid? Okay, that's our next challenge, is how do you make it to look? And there's a few different ways of causing it to act that way. And depending on how you do it, you can get these splash particles. So you could use a variety of techniques. Like, you might want to use marching cubes, or you could use blobs. You could use ray tracing. One thing the SPH has is there's this springiness to it. So that could be unnatural, depending on what you're doing. SPH is really good for splashes and stuff, but it does have this springiness aspect to it. But you'll notice that we have this scalar color field, and I almost think that maybe they're actually kind of talking more like a sine distance function-ish. But over here's another application. We say what happens when you take a scalar field and you take the gradient, you get a vector field out of it. Okay. So the idea here is that you might want to use thresholding on it to determine what the fluid surface is. So you can kind of limit what's happening. Okay, so there's an aspect that once you have the particles, then you have to kind of make it look like the surface of a fluid. So that's another step on top of it. We kind of talked a little bit about finite difference methods already, although I wasn't explicit about it. And the main point here, does anybody know what finite differences are? We kind of talked about them in the class already. Remember we were talking about how you update velocity, and we said that you could do the backward difference or the forward difference or central difference, if you're, like central difference theorem. Remember we were the velocity was changing at different rates, and so some of it would fall faster, some would fall slower. So finite differences essentially is by using these, we're taking, because we have a grid, we're just kind of subtracting these numbers, and we're doing derivatives by just using those basic theorems of calculus. Okay. The semi-Lagrangian method is another method I wanted to just talk about real quick, because the way that you might want to do this is you might want to subdivide it into a grid, okay? And the idea here is that you would apply your external accelerations and integrate with forward integration. And then the next thing is that you update the velocity field. So you kind of take this grid approach. It's technically Lagrangian, but you just kind of use the neighboring particles, I guess, to to kind of do that.
Or you're using the grid to determine the meters?
Yeah, basically. Okay. Then, so you basically separate this whole equation to a series of steps. Okay. So first you integrate your velocity field with your external accelerations. Then you do backtracing to advect the velocity field. Advection is where you're moving the properties around. Then you apply acceleration due to viscosity using implicit integration. So there is a way for us to figure out, using it like an actual formula to say, here's what the acceleration ought to be. There's a lot of math behind this particular method. And then lastly, we project the velocity to a divergence-free field and update the pressure field. So in other words, we pass in the vector field, we pass in the external accelerations, we pass in the density, and we pass in our time step. We do our integration, we backtrace, we integrate again, and then we project and we return the velocity field and the pressure field. And we basically will use that to like evolve the system over time. So it's something we have to be aware of. Okay, so we're just mentioning it briefly, but I think that's all I have for today. Hopefully we learned a little bit more how do you actually get fluids to work. I think we're close with our own simulation stuff. It's just a matter of can we apply these extra functions to it. So I think that's it. So yes.
I'll just check. So how can we focus the hydrodynamics part of things beyond the midterm review? Is that something like more related to us and stuff, a couple more detail? Or
well, the way I figure, it's all fresh in your head. So. I don't think it'll be ridiculous, but if I'm being ridiculous, then let me know. Okay.
So midterm, where, when, how?
9. Oh yeah. So you missed the beginning.
Sorry.
No. Let me real quick. Let me just stop my the OBS thing.